Hey, welcome back. So we're going to finish off the this topic by doing a few more of these practice questions dealing with the reversible isothermal and isentropic expansions. All right, so here's the next question. This time we did one with the isothermal process. Now we're pretty much doing the exact same scenario, this time for the isentropic expansion. So pause the video, work on the stuff, and we'll go over in a second. All right, so to find the temperature, what we're going to want to do is we're going to want to use that relationship. Since we know what the volumes are, we're going to want to use the relationship of the temperature and volume at the initial and final states for an isentropic expansion. We're going to be using this relationship, so plugging in the numbers that we're given, as well as the gamma term for the fact that we're still dealing with a monatomic gas, and we get that the final temperature is a little bit under 200 Kelvin. All right, so for part B, they want to find the change in energy. So that one's pretty straightforward. Now that we have the initial and final temperatures, we can just plug it into our equation for change in internal energy, plug and chug, and we get that it equals to negative 23 joules. All right, now we're still doing a few more questions. So we want to know what's the work done, temperature, and change in the entropy. All right, so pause the video, work and stuff, and we'll go in a second. All right, so once again, this is an isentropic process. No heat is allowed to flow. So the work done, because it's being expanded in a vacuum, that's actually another thing that we didn't really discuss too much, or I don't think we discussed in this class. This is usually called a free expansion. The fact that it's done in a vacuum means that there is no pressure that it has to counterbalance. There's nothing it has to push against. So the work done is zero. Um, and because of the fact that the heat is also zero, that means the entropy change is zero, which means the change in temperature is also zero. So the final temperature is still the same as the initial, it's 300 Kelvin. And then the change in entropy, we can still use that same equation for the isentropic process. I guess since the temperature remains constant, we can actually also consider this as a combination isothermal process as well. Um, and we end up getting the change in entropy as being pretty much the same as the isothermal process we did before. All right, here's another practice question we can work on. Pause the video, work on this up, and we'll go over in a second. All right, so they want us to figure out or estimate the number of accessible states. So the way we're going to end up doing this is by first figuring out what the entropy is. So we're going to take the equation that we have for entropy, the very long one with the ln n over nq. Of course, we're going to plug in what nq, the equation for nq and n is. Um, of course, and we're also going to have to replace some of these with proper terms. Like for example, they don't give us the number of uh, particles, so we're only going to be able to. We have to replace that with pressure and temperature. So plugging the numbers in, we end up getting that the entropy is equal to 3.67 times 10 to the 22. All right. Then what we're going to do is we're going to take the entropy or take this entropy and raise it e to this value, and that will give us the total number of accessible states. So you can write it like this, or if you had access to a high-powered program, you can actually rewrite this to look something more like this: 10 to the 10 to the 22.2. So for the most part, there are a lot of accessible states. All right. Here's the next question. Pause video, work on the stuff, and we'll go over in a second. All right. So it's compressing isothermally, and they want us to find the accessible state. So again, we're going to use the equation that we have for the entropy. So we know that the change in entropy is equal to this relationship. So we already had the entropy in the first case. Now we just need to do entropy in the second case. So solve for that. Plugging the numbers in, again, replacing the n term with the ideal gas law. And we end up getting that the entropy is equal to this, 3.5 times 10 to the 22. Not a huge difference. I mean, relatively not a huge difference compared to what it was before. And what we find that when we do the same idea of raising e to this entropy term, we end up getting a fairly similar number to what we had before. All right, here's the next question. Pause the video, work on itself, and we'll go over in a second. All right, so we're trying to figure out the probability of these particles actually going into half of the container. So what we're going to do is this. Take the probability of it being in half the container divided by the total number of accessible states. And we get that the probability is essentially super small. Yeah, so even though the numbers look fairly similar and doesn't look like it's that far off, because we're talking about such large numbers, it ends up being that the probability of it happening is extremely, extremely small. And here's the next question. Pause the video, work on itself. Remember to try to pay attention to unit analysis, and we'll go over in a second. All right, so here they give us the essentially the frequency of collisions. The frequency is going to be equal to this, the number of collisions times the rate. So they give us, well, once again, the number of particles. We're going to replace the ideal gas law, and then we're going to use that rate in here. And we're going to find that essentially there are going to be in total this number of collisions every second. So within a year, we just, again, play around with the unit analysis, and we get this. So a whole lot of collisions within a year. As you can see, we're trying to build towards a final answer where we're going to actually figure out how many years it takes for this to occur. So pause the video, work on itself. We'll go over in a second. All right, so what we're going to do here, the time is going to be pretty much the probability times this number of collisions. And we get this. So it takes a whole lot of years before we can expect this gas to naturally settle into one half of the container. Yeah, so the universe, if you remember, is only 10 to the 10 years. So yeah, this is an extremely, extremely long time. Which is again one of the reasons why we always consider this this most probable configuration. All right, so here is a quick little summary and rundown of the different types of uh, processes that we've talked about. So we had the isothermal process and the isentropic process, which ended up being things like this of relating the entropy, the work, and the heat, as well as the change in internal energy. A lot of these come from the first law of thermodynamics, setting them equal to each other. The other one was this, the irreversible expansion to vacuum. That was the one that I called the free expansion, the one where pretty much everything was zero. It's almost like a combination of the reversible isothermal and the reversible isentropic expansion together. And yeah, that's pretty much it. So here are the problem sets for chapter 6. So you'll be able to do a few questions dealing with the Fermi-Dirac equation and possibly even the Bose-Einstein equation. Uh, we should be returning to those equations later on. But if you have any other questions, let me know, and I'll see you in the next video.